All right, I'm recording now. Sorry, folks. Folks at home, here's the example I just did. Thank you for reminding me. All right, the limit rules are great. Everybody knows. Okay, let's talk then about this third one. That's what I want to do concerning the limit rules. This is the last thing I want to talk about for these rules, and then we'll move on to something a little different. So it is, we want to show that a(n), b(n) converges to a times b. So let me just write that again. I'll write it as like its own theorem. So it says if a(n) converges to a and b(n) converges to b, then a(n), b(n) converges to ab. All right. Now I gave you sort of a introduction to what we're going to do last time at the end last time. So the proof uses basically two tricks, and one is this weird thing. You know, when you have to do the epsilon business for this proof, you eventually get down to showing that this is less than epsilon, and the proof uses this weird step which involves adding and multiplying the same thing. So not adding, multiplying, adding and subtracting the same thing. In this example, you're going to subtract abn and add abn minus ab. And then this, you do the triangle inequality. Sorry, this less than should be equal. That really is equal. All I did was add and subtract the same thing. And then you do the triangle inequality to split this up. an bn minus abn plus abn minus ab. And then from each of those you can factor. The first one I can pull out bn. So this looks like absolute value bn and then an minus a. And from the second one I can pull out a. It has to come out with the absolute value. All right. So this is the first of what I said, the two tricks. First of all, this thing over here, which we are going to eventually have to make less than epsilon, you do this weird business here to split it up into two things, all right? Why should you like the looks of the two things? Actually, I like the looks of the two things because this one and this one, we can make these very small, right? Because bn converges to b. And so for any epsilon, we can make that part, bn minus b, to be as small as we want. And similarly here, we've assumed that an converges to a. And so this also we can make very small. All right. Yeah?
Should it be an and then bn minus b? Or is it just a?
Over here. Yeah, this is interesting. It's not totally symmetric. Like here I have bn, but here I have just a.
Yeah.
That's what you're indicating. Yeah, in fact, if you want this to work, it must be that way. It came from this because I did minus abn plus abn. Now you might wonder, shouldn't I have done an bn there? But actually, if you do an bn, it won't do anything. You need this thing in the middle to be slightly different from both sides, so that when you split it up, you can do something on both parts. Okay, anyway, can I just say this thing, bn minus b, is very small. What about that? This is not guaranteed to be very small, but it is a specific number. Right? And the bn is unfortunately not a specific number. The bn's is a sequence, and it may be that the bn's get quite large, which could screw up the fact because we're multiplying by something which is very small. But the second trick, so this is like the other trick. That was like first big idea you need to have. And these are not obvious ideas to have. At least the first one is not. This involves just a weird adding and subtracting. The second observation is bn converges to b, so the sequence bn is bounded. This is something we talked about 2 times ago, I believe. There was a theorem that says any sequence which converges is bounded, all right? That's because if it converges, that means it actually, all the terms eventually get close to a certain limit point. That means they cannot go off to infinity, which is what it means if it's unbounded, or they can't go off to minus infinity. All right, so Bn is bounded, which means the reason that's important is, I'll just say, so this Bn right there is not too big. Remember, we intend to show, or we intend to make this whole thing small, like less than epsilon. And you have to make sure that every part of it can be super small. And this is, that Bn is the only slightly weird part. All right? Okay, anyway, armed with these tricks, hopefully we should be able to make the proof work without too much trouble. So I'm going to begin the real proof. I don't know if I can keep that on the screen. I hope you wrote it down. So let's start the real proof over here. We always, since we're showing that something converges to something, we got to begin with let epsilon greater than 0 be given. And then we'll find n, a natural number, such that little n greater than equal to big N implies. Remember, what we're trying to show converges is an bn, and it converges to ab. So this is what we need to be less than epsilon. All right. So now let me write my little sidebar here where I try to figure out how to choose that n. Remember, so we need an bn minus ab to be less than epsilon. Remember this business up here. An bn minus ab is less than that thing that I circled in blue. So if you need to make this an bn minus ab less than epsilon, I'm going to say it is enough to make that other blue thing less than epsilon, because the blue thing is bigger than the other part. So the blue thing says bn an minus a plus absolute value a, absolute value bn minus b, less than epsilon. It's good enough if we can make that thing less than epsilon because it's bigger than the other thing, which we want to be less than epsilon. All right. But now, this is another thing which perhaps you remember from last time. If you have two things added together and you want them to be less than epsilon, you do what we like to call the epsilon over 2 trick. So we will, I'll say, try to make bn times an minus a less than epsilon over 2, and absolute value a times bn minus b less than epsilon over 2. I have two things adding up. They have to be less than epsilon, so it's good enough to make each of the two things less than epsilon over 2. This is the epsilon over 2 trick. And for these two things, actually, the second one is a little easier to handle. I'm just going to divide both sides by absolute value a. This says we need bn minus b in absolute value to be less than epsilon over 2 absolute value a, right? And it is possible to make bn minus b less than that because bn converges to b, and so we can make this less than whatever we want, right? It can be less than any epsilon. So that should be possible. What about over here? Over here we use the fact that bn is bounded. So it's enough, I'm going to say let bn being bounded means bn is less than m. M is the upper bound for bn. Then it's enough to make m times an minus a less than epsilon over 2. And this we can solve for an minus a. Epsilon over m times 2, right? Or 2m, I guess, to make it look like the other one. So all of this is going to come together. This is kind of complicated. All of this is going to come together by saying if we choose the n big enough to make this part less than epsilon over 2a, and make this part less than epsilon over 2m, then everything will work out great. So my actual proof, back to the real flow of the proof, I'm going to say choose n so big that n greater than or equal to n implies an minus a less than epsilon over 2m, and bn minus b less than epsilon over 2 absolute value a. Right? Because the a n's converge to a and the b n's converge to b, we can choose the n to make those things smaller than whatever you want. And so I'm making them smaller than epsilon over 2 big M and epsilon over 2 absolute value a. All right. That was the choice at the end. Can we make the rest of the proof work out? Let's see. So the last part of the proof always says something like, now let n greater than big N greater than or equal to. Then we have, can we make it work? First we begin with an bn minus ab. Maybe I'll let you guys try and finish this off. You have to try at this point to tie together all of this business that we've done so far. I don't know if you'll be able to see if I shrink so that it's all on there. From here, you want to use equal signs or less than signs or something or other and end up with epsilon at the end. Can you see if you can pull it all together? It involves first doing that weird trick where you add and subtract the same thing. And you use some of the other inequalities that we talked about along the way. I'll give you a few minutes. See if you can tie it all together. I don't know if you can see it all on the screen at once. Just barely visible at the top. Not quite. I'll come around and see how it's going. That thing, right? But then you can like anywhere. Start, yeah, first this, and then like this being like so you got to here? Yes. Now you can do like this and let's say we chose this so that this. Oh, this is so anywhere? Yes, so like all right, let's talk about them. I know I didn't get around to everybody. Sorry, this is such a mess on the screen. Maybe it's better if I didn't record this. You begin by doing that weird trick with the adding and subtracting at the beginning, but it amounts to, could I just say, this is, come on now, yeah. This is less than or equal to, what did we end up with? Bn, an minus a plus absolute value a times bn minus b, right? And then what can we do with that? Well, we chose the n so that this would be true. An minus a is less than epsilon over 2 big M. And also bn minus b is less than epsilon over 2 absolute value a. So we can say this is less than, I'll leave this bn like it is. An minus a, I'm going to replace by epsilon over 2m. Plus, I'll leave this a like it is. Bn minus b, I'm going to replace by epsilon over 2 absolute value a, like that. And now, my goal is to keep simplifying and eventually end up with epsilon. What do you think? Well, the a's can cancel, right? Absolute value a here, absolute value a here. Bn and m don't exactly cancel. Maybe I'll just like gather them together. Plus epsilon over 2, right? What can you do with bn divided by m? Did anybody think about this? What do you say?
We assumed m is bigger than bn.
Yeah, bn is less than m, right? That's the point of this m, is that m is an upper bound. That means this fraction, what can you say about it? If the m is bigger than the bn, right? So I can do another one of these. Yeah, it's less than 1, right? That fraction bn over m is less than, I suppose it could be less than or equal to 1. Doesn't matter. Less than or equal to 1 epsilon over 2 plus epsilon over 2, right? Bn is less than the m, which means that part of it is less than 1. And now what can you do? Well, this really is just epsilon over 2 plus epsilon over 2, which adds up to epsilon. All right. This is the hardest of those limit rules, certainly. But this is how we do it. It involves a weird trick. That trick actually is interesting. This adding and subtracting the same thing. I don't know if you remember, but actually that's exactly the same trick you use when you're proving the product rule for the derivative. You use exactly that same adding and subtracting thing. Maybe that's not a big surprise because the derivative is a limit of a product. If you're doing the product rule for the derivative, it involves doing limits of products, which you need the same trick. All right. Great. Are there any lingering questions about this? I hope that you're all convinced that the limit rules are actually valid, and when you're finding limits of things, try to use the rules rather than using the epsilons, because in my opinion, the rules are a lot easier. Although on the homework or maybe on our tests, I am likely to tell you to do it without using the rules just to make you do it with the epsilons. But if I don't say so, use the rules. They're better. They're easier. All right? Excellent. There are, this section in the book, it's called algebraic and order rules for limits. The ones we just did are what the book calls algebraic rules for limits because they involve adding and multiplying. That's algebraic. The order rules are actually quite a bit easier. Well, none of the rules themselves are hard, but the proofs are hard for some of them. The order rules, in my opinion, are much easier. The order rules for limits. That is limits and their relationships with the ordering of the numbers, like being greater than or less than each other or something like that. Here's what I'll just write them down. These are things that anybody would be able to come up with, I think. So they are similar in that we begin with an is converging to a, bn is converging to b, and there's 3 of them. I'm only gonna write down 2 of them. The first one says if an is greater than or equal to 0 for all n, then I'm saying if all the terms in the sequence are positive or perhaps 0, then what can you say about the limit? Anyone want to guess what the conclusion is? If the ANs, the terms are all greater or equal to 0, then A is greater or equal to 0, right? So, on a picture, if you have 0 here and like the entire sequence is over here, they're all positive, then the limit is also positive. It's not suddenly negative, right? Seems reasonable, I think. And the second one is similar but involves two sequences at once. It says if AN greater than or equal to BN for all n. This means you have two sequences and just for every term, the A is always bigger than the B. Then, anyone want to guess what we're going to say for the conclusion? Yeah. Yeah, then A is greater than or equal to B. So if all the A's are bigger than their corresponding B's, then whatever the A's converge to has to be bigger than whatever the B's converge to. Totally reasonable. Again, these are what they call the order rules for the limits. I want to talk about the first one in a little bit of detail, although you'll see it's much easier than the other ones. And I think actually it's helpful to think of the first one similarly to this homework problem that she asked me about can it converge somewhere, but then the limit is like somewhere else or something like that. That's really what this setup is kind of about. If all the values are over here, is it possible that the limit could be over here? The answer is no, that's not possible. I think the easiest way to explain that is in terms of these neighborhoods, right? So I'm going to say let's do the first one. The second one is actually very easy if you already know the first one. So this is the only real in detail proof that we're going to have to do. I'm going to say for the sake of a contradiction, let's assume that AN is always positive for all n, but A, the limit, is less than 0. So the picture then would look like something like, here's 0. Here's the whole sequence is like over here. But for whatever reason, the limit point that it allegedly converges to is all the way over there, right? What's the contradiction? Remember, converging means, so AN converges to A means that for any epsilon, can I just say like this? The end of the sequence, that means like eventually, if we look past the first part, but just look at sort of the, eventually look far down in the sequence, the end of the sequence, I'm not grammatically saying this properly. I want to say all the terms, sorry, can I just erase that? Whoa. I don't know what that is. Turn into Massachusetts or something. Okay, it's better. I got to investigate that. That was a cool button. All right, I don't like the way that I started saying that. For all epsilon, it means that eventually all terms are inside. Can I write it this way just to refresh your memory of this notation? The epsilon of A, that means the epsilon neighborhood of A. It's this little interval surrounding A with radius epsilon in that little interval, all right? Remember, this is the epsilon neighborhood. It's all points within distance epsilon of A. All right? But I mean, it's obvious on the picture that that is not happening in this sequence, right? In fact, in this sequence, all the terms are outside of the epsilon neighborhood, provided that the epsilon is small enough. We should say, if we choose the epsilon to be small enough, then, like certainly if the epsilon is super big, like if the neighborhood goes all the way out that far, then all the points will be in the neighborhood. I don't want that. What anyone want to suggest? What can we choose the epsilon to be to make sure that it's small enough that it excludes all those other points? I want to can you figure out some little number here that is small enough so that all the points in the sequence are outside? This number perhaps will depend on A. I would like one specific number. So it shouldn't involve an. It can involve a, but not an. How about just a, right? If a is over here, that means I'm going to say epsilon less than, would you mind absolute value a? A is negative, so you can't choose epsilon to be less than a. But less than absolute value a, right? This distance here would be absolute value of a. And we just want the epsilon to be smaller than that. This will automatically be smaller than an minus a, which is what you said. But I don't want it to depend on n. It's just one specific value. So if we choose epsilon to be less than absolute value a, then we can just, it's obvious from the picture, then all terms are outside this epsilon neighborhood, right? Because they're all to the right of 0, which is far away. So an does not converge to a, and that's the contradiction, because the assumption was an does converge to a. All right. All right. I'm glad to see the neighborhoods again for a few moments. Okay, so if all the terms are positive, then what they converge to are positive or 0. Then what they converge to must be positive or 0, right? Can we say something about this? It says greater or equal to 0. Is the same thing true if it was just greater? So I'm wondering, is it true if an greater than 0 and an converges to a? Is a greater than 0? Is that true? Or is it possible that you have a bunch of things that are bigger than 0? Can they converge? Is the limit automatically bigger than 0? No? Somebody say no? They're just shaking heads. No? Why not?
Because you can have a sequence that's going down and down and down and never actually get to 0, like 1 over n.
Yeah, right. So actually this is not true. This is false. And a counterexample would be 1 over n converges to 0. Right? Here the sequence, these are all greater than 0, but this one equals 0, right? So it is not true that if all the terms are greater than 0, then the limit is also greater than 0. It is true, because of the theorem we just showed, if they're all greater or equal to 0, then the limit is greater or equal to 0, right? It's not true with just greater than. Okay, great. Can we talk? We got 6 minutes left. Let's just talk about the second part of that theorem about order rules for limits. Remember the first part was if they're all greater or equal to 0, then the limit is greater than or equal to 0. The second part, if an greater than bn, there's a trick here. So I'm just going to say number 2 like that, follows using number 1. Check it out. So I want to show that b minus, what? B is less than, I forgot what it, b is less than a, or a is less than b? A great, okay, so, come on. The eraser is slow. If an less than bn, is that what it said? No, it's the other way around. Sorry. It doesn't really matter, but I might as well say it the same way. An greater or equal to bn, then a greater than or equal to b, right? You can do a simple trick and then use the result from part 1 to get the result of part 2. Here's a simple trick. Part 1 is used when a sequence is always greater or equal to 0. Are there any thoughts about how we could somehow transform this, an greater than or equal to bn? Can you change that into saying something or other is always greater or equal to 0? That's what I have in mind. because I want to use part 1, which applies when something is greater or equal to 0. So, any thoughts? Can we do something with an greater than or equal to bn? Oops. An greater than or equal to bn means I want to write like this. Yeah.
Subtract the n from both sides.
Okay, yeah, subtract bn from both sides. An minus bn greater than or equal to 0. All right? And then we use part 1. Then by part 1, we get, what's the conclusion that part 1 would say? It says if the sequence is always greater or equal to 0, then the limit is greater than or equal to 0. So what would that look like?
E minus b greater.
Yeah, by number 1, it means a minus b greater than or equal to 0. Because the limit of an minus bn is a minus b. That's because of the limit rules about adding together two limits. And then what does this mean? Then we can just add the b back on both sides, and it says a greater than or equal to b, which is what we wanted. So this is what I meant by saying number 2 actually just follows easily if you already know number 1. All right? Excellent. That's about it. Can I just give you 2 more real quick things that we don't need to really do the proofs of these, but I just want to have them written down. Number 1 said if an is bigger or equal to 0, then a is bigger or equal to 0. There's nothing actually special about that number 0. This is true for any constant. So I'm going to say, let me say it this way. For the same reason, I don't want to go through the proof of this, but if an is bigger than or equal to c for some other constant, it doesn't have to be 0. 0 is not a special number in this sense. Then the limit a is greater than or equal to c. All right? This is true for any c, a real number. All right? That was one. And then the second one I had to say was, oh yeah, all these are also true with less than or equal instead of greater than or equal. So for example, if an is less than or equal to 0, then a is less than or equal to 0. And if an is less than or equal to c, then a is less than or equal to c. Right? This for the same reason, only on the other side. All right? And the same proof is what you use to demonstrate these other ones. All right? These are all the order properties of the limits. All right? And I think that will do it for today. We'll do it something different next time. All right, see you then. Sorry for the folks back home. I forgot to hit the record button in the beginning. Probably wasn't any good.